What's your secret? Tell me.
By studying the quark-gluon plasma, you also go back in time because you go back to the early universe.
Super challenging, and I find a crazy but wonderful idea. They asked me for that.
Quantum mechanics. A guy named Heisenberg, not the one from New Mexico, but the other one.
And then I made my magic machine.
Yeah. Hello, everybody, and welcome to Early Morning Coffee at CERN. My name is Stephen Goldfarb. I'm here with two of my colleagues to talk about a very interesting topic, the collision of heavy ions in the LHC. Joining me is Reyes Alemany, who is actually one of those magicians I often talk about, working on beam operations, right?
Right.
On the LHC. And so it's going to be a pleasure to hear how these magicians actually managed to get beams to go 27 kilometers around and then at a specific nanosecond to collide in the dead center of our experiment. So I have a lot of questions for you. And also with us, we have Marco van Leeuwen, who is the spokesperson for the ALICE experiment. ALICE is really specialized in heavy ion physics.
Yeah, right? That's right.
And I'm really excited to hear about that because actually I should, full disclosure, I used to work on an experiment that was in this magnet, this beautiful magnet here at ALICE. And I'm a little sad to see you tore that experiment. It was called the L3 experiment from back in the day. But the new one you've put in there is fantastic and it's given us a lot of really, really good physics.
It was getting a bit old. We replaced it with something more modern.
Something more modern. That's the way it goes around here. So, okay, so I'm gonna turn to Reyes here because I have a lot of questions for you. Normally, you know, the LHC is called the LHC and not the LPC, right? Why would I say that? The LHC stands for Large Hadron Collider. Most people know that we're colliding protons. So why didn't we call it the Large Proton Collider? Well, because we collide other things. And among them are heavy ions, lead ions we do most of the time, right? And so when we collide these lead ions, it's a mean that we've taken off, an ion means you've taken off some electrons from an atom, and which means it's charged, right? And then you can have them collide. And we do this because we would like to study the early universe. People like Marco and his colleagues would like to be able to look at the collisions that are formed there and look way back in time before a microsecond after the Big Bang, somewhere around there.
Yeah.
Way back. I don't remember. I wasn't even a student. Yeah, when we weren't around back then. Sometimes I feel like I was, but so around that time, we had really, what is it? The whole universe was in a hot, dense state. Yeah, that's what they would have said on Big Bang Theory. But it's true. We had this sort of plasma, quark-gluon plasma. So we're relying on Reyes to give us beams that can make this quark-gluon plasma, this primordial soup, and a very, very hot primordial soup. We're talking about trillions of degrees, millions of degrees. So a very hot, so you need to let that cool down for a bit, which we did 13.8 billion years before really, looking at it. So, okay, let's get to the questions here. So Reyes, how do you do this? You're taking lead. In the old days, this pencil had lead in it. You're taking lead and you're somehow heating it up and making ions out of it and colliding them. Can you walk us through this?
So what we do is we take a piece of metal, which is pure, almost pure lead of 208 nucleons, not 207, not 209, 208.
208, okay, 208.
And what we do is we put it in an oven. It's a very small piece of metal, maybe this size. We put it in an oven, and then we heat it by 800 degrees. And then the atoms start to escape from this piece of metal, and they start to get ionized. And we build a kind of plasma. And in the plasma, we have the ion of the lead ions. So now they are charged, because only charged particles you can accelerate with electric field. So that's the beginning of the journey. So these ions are accelerated through electrical fields or potential differences through the whole accelerator chain, which is first a linear accelerator.
Okay, so a linear accelerator means it's in a line?
Yeah, it's straight. It's more or less 30 meters long. And then we get to the second stage, and this is the low energy ion ring, which is a circular accelerator where we accumulate the ions, because when you take particles out of metal, this is not very efficient process. You don't get a lot of number of ions, so you have to stay there for quite some time accumulating in this low energy ion ring.
So you managed to keep them somehow. So they're in a kind of magnetic field or
yes,
field?
so this is a vacuum tube. They are circulating inside, and with magnetic fields, we keep them going around, and with the electric fields, we accelerate them. We give them a kick every time they pass by, and that's the way they gain energy.
Oh.
So once we have enough lead ions for Marco, then we accelerate them and we extract them to the next accelerator, which is the proton synchrotron. So here what we have done is to get all this bunch of ions, 800 millions of them.
Okay.
We have split them in two, and we have sent them to the proton synchrotron. There, each of the bunches gets split again.
How do you split bunches? I bet that's complicated, huh?
So now the magic comes from the radio frequency cavities. These are electric fields that oscillate with a high frequency. And what you do is to create potential pits. Like if you dig a hole in the sand of a beach and you put little balls there, they are in a potential pit, but done by gravity.
Okay.
But you can do the same with electric and magnetic fields. So the electromagnetic field, you can create these potential pits. And there, our ions, when they are trapped inside, they are happy and stable.
They're happy because they're one charge, and you have this potential which attracts them.
Attracts them, right. And then they are not going away from our vacuum chamber. So you have many of these potential pits, as many as is needed, and they are running around the accelerator, and every time higher speed, higher energy. So now we have 4 bunches that we ship to the next accelerator, which is the super proton synchrotron.
It's really, I should note here that we're kind of going through history, right? The proton synchrotron was one of our first accelerators. So now we're using the PS to inject now these heavy ions into the SPS?
Yes, yeah. So the SPS, so the PS, the proton synchrotron sends to the SPS 14 times 4 bunches. So this makes 56 bunches. And there, before we accelerate to send it to the LAC, we take half of the 56 and the other half, and we slip them longitudinally on top of each other to make the bunch separation. So each of the packages that before was 100 nanoseconds, which corresponds to 30 meters if you are running at the speed of light, to 15 meters apart. And then each of these 56 bunches that now are 15 meters apart, they are finally sent to the LAC. And we send 22 times 56, 2 times for one beam and for the other beam.
Okay.
So once they are in the LAC, then we accelerate these ion beams, and Marco is super excited.
Yeah.
Because very soon we will put them into collisions.
Yes. Wow, that's a long process. Now these go and they collide at all 4 experiments?
Yes, we are providing collisions to our clients, LACB, ALICE, Atlas, and CMS.
Okay.
Yeah.
I know we get them at Atlas, and we're happy. We've done measurements with them. But I also know that Atlas is really specifically designed to look at these kinds of collisions. So maybe Marco can tell us a little bit about what you're looking for and how you go about looking for it.
Yeah, so the Alice experiment, our detector, is designed specifically to look for the quark-gluon plasma and to study what we call the strong interaction, the interaction between quarks and gluons, which are inside the protons and the neutrons, which are again inside the nuclei, the lead nuclei that we collide. And what we look for specifically is this very hot soup. So we look for a phase transition between normal nuclear matter and molten nuclear matter. And then we study the properties of the molten nuclear matter of the quark-gluon plasma, which is then also the properties of the universe about a microsecond after the Big Bang.
And you give us really great collisions on the inside. We never get to actually see those collisions directly, right? So this is quantum mechanics. A guy named Heisenberg, not the one from New Mexico, but the other one, he tells us, you can't get in there. There's a certain area we're not in. So that's what's common to all of our experiments, right? We build them the best we possibly can to see as close as we possibly can to the interaction point. But we will never, ever know exactly what happened on each event. And that's a good thing. I just wanted to reiterate that because I find that really cool. It's one of the things that got me into particle physics. It's a statistical measurement. So you're measuring all in Alice. You're looking at the shapes of the distributions of the particles that come out, the different charges, I imagine, and you also another concept you mentioned in there, which maybe you also mentioned, Reyes. We said plasma. I think I did even at the beginning too. There was a quark-gluon plasma at the beginning. Maybe who would like to explain what a plasma is? Because it's a hard concept. It's not a state that we're used to.
So plasma in general is a gas of charged particles, and you make it by heating things up, and then the internal collisions become so violent that things break apart. And the plasma in the source is in what you would call an electromagnetic plasma. The charges are positive and negative electric charges. But the quark-gluon plasma is a plasma of the strong interaction. You have quarks and antiquarks that are flying around, and the charge that comes with that we call the color charge. It has different properties than the electric charge, but you can think of it loosely as something similar. So opposite charges attract, but it turns out that in the color charge, in the quark world, there are 3 different charges, and each has a positive and a negative, and they all attract each other. So it's hard to think about this interaction in terms of what we are used to, because we are used to charges either attracting or repelling each other. But, for example, gravity, you only have attraction. And here you have, in practice, also mostly attraction, but it's much stronger, and you can, for example, not pull a quark out of a proton. So the only way we can make a plasma is by kind of compression, by just producing so many quarks and gluons in the collision that the distances are so small that they can move freely over what we then call a relatively large volume. It's the size of an atomic nucleus, which is, of course, in absolute scale, is very small. It is 10 to the minus 15 meter. So it is less than a billionth of a meter. So it's really very small. With a very high temperature.
Yeah.
And I think one interesting thing of the LHC is that because we have such a large energy, the lifetime of this plasma is relatively long, is longer than at lower energies where previous experiments took place. And the other very interesting fact is that at the LHC, the energies are so high that we can produce heavy quarks. Protons and neutrons are made of what we call light quarks, up and down quarks. And then there's a third one which is called strange quark, which we often also consider a light quark, but then you have charm and beauty, and then the top quark, which you said lives too short to be of practical use in this context. But the charm and beauty quarks are interesting because you need a lot of energy to produce them, so you cannot produce them inside the plasma. You produce them when the 2 nuclei meet in what we call hard interactions. And then you have these heavy quarks, and they go through the quark-gluon plasma as it cooks around and expands. So, and then by looking at these heavy quarks, which you can identify because they have a very characteristic decay signature in your detector. So in your detector, you see, this particle contains a heavy quark. And then you can trace back and you can say, okay, so what happened? How much kicks did it get from the plasma?
Okay, so now I want to get back to the magician here, because we often ask her to do the impossible, and your team. Reyes isn't the only one working on it, but an important person working on it. We asked you, can you make these collisions perfectly, get these two beams to hit, right on each other in the center of our experiments, and then we come to you and say, you know what, we have an idea. Could you just have these two beams miss or slightly miss each other? And you smile and you say, yeah, sure, no problem, right?
So, in fact, this is something that happens very often, that the experiments would like to reduce the amount of collisions per interaction that they have to process. And this you can make by separating the beams at the interaction point. And it's also very interesting because you can separate the beams by very precise amount, and you control this with dipoles, dipole magnets. So they tell us by how much they want to be separated, or in using a very specific quantity, which is called pile up, the number of collisions per crossing, and then we calculate how much beam separation this corresponds to.
Okay, yeah.
And then we separate the beams, and this separation in millimeters or micrometers is translated into current in a magnet. And finally, the magnets go to this current and the beams separate.
They separate.
And then in this case, we don't collide the core of the beam, but we collide the tails, the particles that are at the outside of the core.
Okay.
And this is also very nice because then we can consume less fast the beam, so the beam stays longer in collisions, and we can give physics for longer time. And as the tails are being consumed, they are automatically repopulated by the ions at the core via a diffusion process.
Okay.
So that's the way it works.
Okay, that's really nice. I mean, one thing, you mentioned pile-up, which is actually a really important thing for everyone. I think probably we get more in proton collisions, but there's pile-up also in heavy ions. So you're taking and dividing up these nice little bunches of protons or of heavy ions, putting them on the train to go around and smash into each other.
And so there are 208 nucleons, protons, and neutrons together in each heavy ion collision. So in some sense, when you collide two ions, you get the equivalent of 40,000 proton-proton collisions in one go. And this is valid, for example, for the number of jets. Then that number really matters. But we get, while in Atlas and LHC during the proton running, you get 40 megahertz times 50 collisions, so 2,000 megahertz of collisions.
A megahertz is like millions per second.
Yeah. For heavy ion collisions, we get 50 kilohertz, so we get 50,000 collisions per second.
Okay.
But each collision is like 40,000 collisions individually.
That's a huge,
but it happens at once. So we get, in one collision, depending on whether it is a central or a non-central collision, we can get up to 5,000 or 10,000 particles in the detector. And the detector covers only a part of the total collision, so tens of thousands of particles are produced in a central collision.
How is Alice is, I think, specifically built to be able to handle this very fast rate? Handle lots of particles. What's your secret? Tell me.
Well, it's always a matter of optimization. It's always a matter of optimizing for a certain type of collisions. And so Alice is optimized for getting collisions with very many particles. And one of the elements that we optimized by is by having a detector which we call a time projection chamber, which is a very large volume. It's a 10 cubic meter filled with gas, and the gas, it's neon CO2. It's a mixture of gas. That gas acts as the detector, and
Okay.
You can then read this out with kind of cubic centimeter resolution. So you have a very large volume where you get very precise hits, and you can that way you can separate a large number of particles in each collision. So we have designed a detector to be able to measure about 20,000 particles per collision. Then it turned out that the total number of particles that we produce is a bit lower than that,
Okay.
which makes it easier to detect every collision.
Jenna had asked me a question earlier on, which I think is a really good one to ask. And it's one for Reyes, is things that we collide in the LHC. So we talked about protons, heavy ions, which is lead at the moment. Have we collided other things, and do we have plans to collide even other things in the LHC?
Yes, indeed. We have collided at the LAC already in 2017, xenon against xenon. We also injected and brought to stable beams, so flat top or highest energy, ions that kept one electron, so lead 81 plus instead of lead 82. This was a very first experiment ever done at the Large Hadron Collider. And what else? Next year, we are going to collide at the Large Hadron Collider, oxygen against oxygen,
Okay.
and proton against oxygen, to study on one side the quark gluon plasma with a small system. Oxygen is 16 nucleus.
Yes. That's much smaller than what we've been doing.
Right.
And it will that give us a quark gluon plasma?
That's a question we are anxious to find the answer to. So we see in lead-lead collisions that every collision produces a quark gluon plasma. So in that sense, they are all a bit the same. We get a very high temperature. And we would like to know what are the limits for quark gluon plasma formation. And you can do in temperature, but you can also go in volume. And oxygen is quite a lot smaller with only 16 nucleons. And I think there will be a quark gluon plasma, but it's not settled. And we would really like to see whether we can find evidence for a plasma. Then there are two elements which we discussed before. One is this expansion of the fluid. And we even see in proton-proton collisions, specific collisions where many particles are produced, we see some signatures of this non-uniform distribution, which we know in heavy ion collisions comes from pressure gradients. In proton-proton collisions, we don't think there should be pressure gradients, so we are not sure where this asymmetry comes from. So this we will probably see in oxygen collisions. But the other signature that I talked about, this energy loss, this Dijkstraat asymmetry, or the energy loss of heavy quarks, we don't know whether this will be visible in oxygen collisions. So this is one of the big questions for that run. And we can then, in a few days of data taking, we can collect enough data to have a good look at this. So this is really something where we have an open question and we have to experimentally attack it. We have to try and see.
Okay.
And for us, it's very challenging because will be the first time that the machine delivers two operational ions in the very same year. So we will do this around June.
Yeah.
So around June, the collisions, oxygen, and proton-oxygen are foreseen for LAC. And then we will switch to lead. So we will remove the oxygen from the plasma, then put this lead and start to heat and produce the lead plasma. And then at the end of the year, we deliver lead collisions to the experiment. So we are very much excited because it's a lot of work.
That's good. I imagine it's a lot of, you don't need to just stick them in. Okay, let's try some other element and stick it in here. There's one thing I want to come back to, because I find it one of the coolest things that I saw, and I love to show this when I give a public talk, is you mentioned that sometimes, we're making these collisions sort of just miss each other. And one of the coolest things, I think, I would call it like the Star Wars collisions, is where we actually, you took the heavy ions and they actually only peripherally very peripherally hit each other. So photons, these photons that were surrounding the heavy ion, because it's a charge, big bunch of charge there. When there's a bunch of charge, there's photons that come along with it. We're zapping through other photons. And while lightsabers look really cool in Star Wars, they're taking photons, zap, 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 and you can hear them. The reality is it would be very quiet because photons miss each other most of the time. I mean, pretty much all the time. It's very, very rare. But will you manage to give us beams where the photons interacted?
Well, this actually you can get even if you are providing head-on collisions, because out of these head-on collisions, there are always ions far apart, such the photons that come with, they do this type of interactions, right? So you don't have to separate the beams to get this. This comes for free. So this is part of the physics that they are also doing.
And it's very cool to see. If you look at the event displays, normally your event displays, even ours when there's heavy ions, it's full of multicolored tracks. The inside is completely filled with tracks. And in this case, you often see nothing on the inside. And suddenly, a couple particles. It could be the very first time I saw this, it was 2 photons. So it was photons that scattered off each other. You just saw photons coming out. But since I've seen all sorts of different things, including taus, for example, or charm, or different things.
Often just 2
out.
particles, because you have a photon hitting another photon and making 2, in that case, mostly photons, or you have a photon hitting the nucleus, but this is just a photon. You often produce just a quark and an antiquark, or 2 leptons, a tau and an anti-tau, or 2 muons. And these are very contrasting with our very full event display.
Yeah, they're beautiful.
Finding these collisions between the other collisions is challenging, because you get many collisions with many particles, and then sometimes you have a collision with just 2 particles. And when you have optimized your detector settings to handle all these many particles, sometimes you may overlook a collision where there's just 2 particles, but we manage.
Sure. It looks so nice and clean. Before we go, actually, I want to ask you guys both a bit about the future. What does the future hold for us? I know that for the LHC, we have 2 more years of running, and then we're going to tear, some of us at least, will tear our detectors apart completely. We've been working for years now to prepare new detectors to stick inside, to upgrade them so they have higher resolution, spatial resolution, time resolution are better, in order to handle the high luminosity LHC collisions, which have even more collisions per second, right? What's in it as far as heavy ions go? What can we look for in the future for heavy ion collisions?
So there are different requests. So the most important one, of course, comes with the upgrade of ALICE, when they will do the ALICE 3 detector, which will be designed to be able to process even more collisions per crossing. And they are asking us, the machine, to provide more collisions per crossing. So with lead, we are at the limit. We think we could make some little steps to gain a little bit here and a little bit there. But we think the future is with lighter ions than lead. And with that, we might be able to give them more collisions per crossing, more luminosity as the figure of merit of a collider like the Large Hadron Collider. So we are preparing already for that. And because not only the Large Hadron Collider is our client, we have other clients like fixed target experiments in the SPS North Area facilities. And they are asking for boron, magnesium, and oxygen. They have a very nice program, physics program, with these 3 ion species, and we are preparing for them as well. This year, we tested magnesium up to the extraction of the proton synchrotron, and then we started with the lead. And last year, we tested krypton, which is one of the ion species that might provide higher collision rates for the experiments when this future comes.
Okay.
And but we've been also asked very super challenging, and I find a crazy but wonderful idea, is to put different ions in the same beam.
Ooh.
So how do you do this?
We don't ask you enough, huh?
They asked me for that. So they want to have in the same beam, in two beams of LHC, a combination of oxygen and neon bunches.
Oh,
Such we can do oxygen against oxygen, neon against neon, oxygen against neon,
oh yeah.
and neon against oxygen. So you have all the possible combinations in one single field in the LHC.
And they just ask you for this.
So they ask, and then I made my magic machine.
Yeah.
And then I come with a solution.
So what I'd like to know though is how many times does he then come to you guys with a bottle of champagne in the CCC in the control center there?
Many times.
Many times.
They are very nice.
We're very appreciative. The experiments, we always do this when we hit a milestone, when they give us really great beam, bottles of champagne. And they never turn them down. You guys never ever turn them down. So for Alice, I heard this phrase Alice 3. Is that something that's being thought about?
This is our future perspective. I should say that you mentioned that Atlas and CMS are now doing very large upgrades in this long shutdown. We actually did a very large upgrade in the previous long shutdown in between 2018 and 2022. We took out most of our detectors and replaced the inner part of the detector with a new inner tracking system, which is a kind of digital pixel camera for the collisions. And our pixel camera has about 10 billion pixels in 7 layers. So that is a new, that was an upgrade, and that allows us now to read out these 50,000 collisions per second, which in the past we couldn't measure all of them, basically. So we are now in the phase of what for us is already a kind of a high luminosity, more statistics, better precision to identify the heavy quarks that I mentioned before. Then we will do smaller upgrades in the coming long shutdown. So in 2 years from now, we have a few tweaks that we want to make, a few smaller detectors that we will be adding. And then 4 years later, 4 years after the next long shutdown, we are making plans for a large upgrade, for a replacement of most of the detector systems to improve the pointing precision, to be able to identify these heavy flavor particles, and in particular also particles that contain more than one heavy quark, which are at the moment there's a very few of them, so you need a very precise detector to measure them, and they will tell us even more about how we go from kind of a chaotic collision to something that looks like a fluid which is in thermal equilibrium, which is like a regular liquid where everything collides with everything all the time. And that takes time, and we want to understand in a collision at the LHC, how close do we get to thermal equilibrium?
Okay. Well, it sounds like you have a full physics program planned out in the future, and you've apparently got your work cut out for you, thanks to people like this, like Marco. So anyway, I want to thank you both for coming on the show today on Early Morning Coffee at CERN. We have with us Reyes Alamini from CERN's Beams Operation Group, and also with us Marco van Leven, who is the spokesperson from the ALICE experiment. So thank you very much, both of you, for coming on today. This has been Early Morning Coffee at CERN, a podcast by the scientists of CERN about the science of CERN. You can find all of our episodes on the CERN YouTube channel and also anywhere you get your podcasts. I also want to give a shout out to those of you who give us comments on our YouTube channel. I read them all and I found them very interesting. Our last podcast, which was on dark matter, there were some questions about dark energy. So thanks. Bring us those questions and your comments. They're greatly appreciated. Our editor and producer is Chetna Krishna. Our executive producer is Jacques Fichet. Ron Saukerbulk is our technical lead. Our studio manager is Max Bryce. Sound engineering by Piotr Trakzik. Our original theme comes from the Kinets Blues Band. piano by Wojt Play and Niki Krajewski. Many thanks to Paolo Catapano, Matthew Chalmers, and Arno Marcellier, who are giving us lots of great advice and strategic planning. And a big thanks to the entire education, communication, and outreach team here at CERN for giving us access to this wonderful wire chamber studios and all the help that comes with it. Opinions expressed here are our own and do not necessarily reflect those of CERN or our colleagues, although I think they ought to. My name is Stephen Goldfarb, and this has been Early Morning Coffee at CERN. We'll see you again soon.